we decided to take a spectrum with one of the telescopes, which basically allows us to take the light we see and break it up into its colors so we can see what it looks like at different colors. And this is incredibly valuable to really understand what's going on with the physics of the objects themselves.
That data that Josh had the quick thought of, getting the spectrum right away, I think will be extremely important, is extremely important already, and will continue to be going forward.
Something else this might have been is it just happened to be a supernova that was there that, the previous image we looked at was from months ago, and maybe it's something else that had happened but not related to what we're looking for. But this didn't look anything like just a random supernova spectrum, which would have lots of different lines and bumps and features from different elements you can see. So this was clearly something very different, and we could tell that right away.
From ground-based observatories, I think that those spectra will end up being the most unique observation of this object.
These events are something that theorists have been studying for a number of years, almost the last decade, really, trying to predict what such mergers would look like. Neutron star mergers are likely the source of most of the heavy elements in the universe. So elements that are produced by what's known as the Rprocess. R is for rapid bombardment by neutrons. So these are elements like lead, gold, europium, uranium. All the heaviest elements in the periodic table are primarily produced by the Rprocess. And for many decades it's been a mystery as to where Rprocess elements actually come from, what kind of astronomical objects make them. Over the last few years there's been a consensus emerging that they're probably from neutron star mergers.
So this has been thought of for a long time, that this is an environment where you can make these materials. Why theoretically you expect the neutron star merger to be very red is because if you make these materials, you can make a particular group called Lanthanides, the elemental table to figure out where that is. These have a huge number of transitions that are available to them, and so they're very good at absorbing optical wavelengths. So if you have material and you create these lanthanides on the outside, it just will absorb anything in the optical, and you just will only see them at longer wavelengths in the infrared then.
This was largely driven by theoretical calculations and by indirect observational evidence, because nobody had actually seen a merger of two neutron stars, and so we couldn't verify directly that indeed they were producing large amounts of Rprocess elements. So that's one of the things that we are hoping to determine conclusively.
So that was a theoretical expectation. But we saw instead that at very early times, the first about 2 days, it was extremely blue.
It was incredibly smooth. So it was much brighter in sort of bluer colors, and then it got fainter to the red, and it was incredibly smooth. It just sort of looked like a swoop.
And then it turned red. And so at the end, or what our study argues, is that it looks more typical of what you expected theoretically, but the early times were very blue, and there are some models that people are working on right now to try to explain this. It's not clear physically what's going on still to date with the blue component. There's a couple different competing ideas. And so why is it blue in the beginning? Why don't you have these lanthanides in the outermost layers that you see in the very early times? These are all the type of questions that we're trying to figure out.